So now that we have our settings dialed in for each of the materials in each of the tools, we're ready to do a multi-material print. So I'll come into SolidWorks here and look at this model that I'd like to print first. So this is just 4 revolutions about a center axis here. And if we look at this sketch, you can see that it's not very interesting, but it'll give us some more information and give us a starting point for our multi-material print. So the width of the cylinders and their height will give the print heads a chance to do the infill settings that we have defined. And that's something that we didn't see in the thin-walled print that we did to dial in the settings for each of the tools. So that'll give us a little extra information. Then what we're also looking for is how well does the machine maintain the interfaces between materials. So we're basically checking our X and Y offsets there. And then on the top surface, how smooth is that top surface? So basically, do we have our Z offsets set correctly? But then the real thing that we're looking at is how well does the machine switch from one material to the other. So we'll follow the same steps, exporting this model to STL files in order to be able to bring them into Simplify 3D. And so just to repeat the process that we have before, even though in this case it was kind of unnecessary, I created a coordinate system on the bottom surface of the part, and I'm going to use that coordinate system when I export the STLs. So the other thing that I did, though, was create different configurations for each of the tool heads that I'm going to use. So my T3 configuration is just this portion of the model, T4 is this portion, T5 is this portion. And the way you do that is just to take your default configuration, right-click, say Add Configuration, define a name, and then go to the model that you want to keep or the models that you want to delete, and then you can go into Insert, Feature, Delete, Keep Body, and then you can decide whether you're going to delete a particular body and keep the others, or keep the one body that you have selected, say OK, and you're left with only that body. Now, when we go to export this, let me just delete that now. Let's see. So I'll select a different configuration, grab the one I just created, delete that. So when I go to export my model as an STL, I want to be in the configuration of the model that I'm trying to actually export. I'll say Save As, select STL, and then in my options, I want to select that coordinate system 1, say OK. And now the default file name is going to come up. That's the file name for my model. I'm going to say -T3, T3. And then same thing, switch to my T4 configuration. And in this case, I want both of those models. So T4 is PVA, that's my support material. So I want to confirm that the support material bonds well to the bed. We'll talk about that in a minute. But I'm going to print a base underneath the other components to make sure that it both bonds well to the bed and those other materials bond well to it, because that's what's actually going to happen in the part that I'm printing. So I have those two models, the base and then that center disk. I'll say File, Save As, and then STL. And it will have that coordinate system 1 already selected because I selected it for the last time that I said Save As. So we're good there. We'll just call this -T4. And then same thing for T5. It's just that outer ring. Coordinate system 1's good. So then my -T5. Save. Yes. Yes. Then in Simplify, I'll bring those models in. So I have these 3. I can select them all, bring them in. And now Simplify auto-arranges them, thinking I'm going to want to print each of these parts separately. So I'm going to select all three of those. So just Shift, Select, and then go to Edit, Align Selected Model Origins. That will align that coordinate system 1 of all of those files that I saved and center the part and put it on the bed. And if we want to check how the coordinate system of the parts compare to the coordinate system, the base coordinate system in Simplify, we'll double-click the part, and you can see here my X, Y, and Z offsets are all 0 for all of the parts. So we're good there. Now we need to grab the particular parts that we want to print with the tool heads we want to use. So I'll double-click on my T3 process, say Select Models, select None to make sure that I don't have anything else grabbed, and then I'll choose the model for my T3. And that's the nice thing about naming the parts with the tool head that you want to use. This portion is much quicker. Okay, and then T5, select model, grab my T5. And then I'll select the processes that I want to use to print. Select all these, say prepare to print. And you can see that they're highlighted here. Now, we want to double check that we've switched back to continuous printing layer by layer. If we did switch over to sequential printing, this would cause crashes because these parts overlap. If the machine tried to print them one at a time, it would print up to a certain height, then it would come back down and try to print the lowest layer of the next component and would crash into the material that we already put down. So that's one of those ones that you have to be careful to double check when you go to do a job after you've done sequential printing. And then in Simplify, there are the different things that you can see in your preview. We want to check our active tool head and make sure that we actually are using the tool heads we think we are. And then we can come down here and kind of walk backwards in our print and make sure that the tool head color corresponds to the actual model that we think we're going to print with that tool. And you can see here in my PVA settings for Tool 4, I chose 0 floor layers. And the nice thing about that is that when you go to put this part in a water bath afterwards, you'll get water into all those cavities, and it will dissolve the support material much more quickly than if you had a solid layer on the bottom that the water had to work through first. So my preview looks good. I'm going to say Save Toolpaths to Disk, and save this as my 3-material disk.g-code. And then I'll go to our diabase printing wizard and set my my standby temperatures for each of my tools. Now I already have these set from the previous prints that I did, and my preheat times look okay, and I have auto clean checked for all of them, so it should every tool change prime and clean the nozzle before it starts printing. So now I'll go and select my file. So this portion of the printing wizard allows us to go back and make a few more changes to our settings if we choose to. So say for Tool 4 on the first layer, I may want to slow it down more than I have in previous prints. So let's say we'll slow that down to 80%. So this doesn't actually change our G-code setting for our speed. It changes our speed factor in our controller. I'll show you that when the print starts. And then we could change our extrusion factor if we wanted for that first layer to really push out material and make sure we got a good bond on the bed. I'm pretty happy with the sample parts that we printed with PVA first, so I'll leave that alone for now. So then we'll save that toolpath, just overwrite the previous file, and then we'll come to our controller and upload that G-code. Now, before we start this file, though, we do have to prepare the bed for the material that we're going to use. So one of the more frustrating aspects of 3D printing is trying to get good bed adhesion with your different materials. So PVA is a good support material, but it can be finicky, and you have to prepare the bed well in order to get it to actually bond. So what we're going to do is just take a piece of medium grit sandpaper, so this is about 120 grit, and just rough the surface of the Kapton in the area that we're going to run the print. Now there are plenty of other ways to deal with this. There are a lot of different bed materials out there. We like a thick layer. I think this is a 10 mil layer of Kapton, and it's a very versatile bed material. And we typically use urethanes, which bond very well to Kapton and allow us to use acetone to remove them. So for what we do around here, this is typically the process that we use. For PVA, though, you need to rough the bed up and then apply. This is just a 1-to-1 mixture of water and wood glue. So we're using this Tight Bond wood glue, which is a PVA-based adhesive. A lot of people don't like to use adhesives on their bed because it can get dirty and get out of control if you're not diligent about cleaning it every time, and if you're not careful when you actually apply the adhesive. So if you just apply straight wood glue, it builds up a thick layer, but if you have a 1-to-1 mix with water, it's just a thin layer that gets applied, and then the PVA grabs well to that. So the adhesive gets down into the cracks that we created with the sandpaper and bonds tightly there, and then the PVA bonds well to this material. Now in this case, I also have my bed set to 50 degrees C. I can either do this in the G-code or I can do this here in my controller. Okay, we're ready to start this print. I'll say yes. And the machine will heat up the extruders, prime the nozzles, and start. So one of the first things that we want to check with multi-material printing is that our nozzles are priming and cleaning correctly. So there is quite a bit of adjustment that we can do to the cleaning station. They should be fairly well dialed in when we send the machines out, but if you crash a nozzle and bend the heat brake and then run a cleaning cycle, that can also knock the cleaning station out of whack, and some adjustment will be needed. So we'll go through most of that in a later video. I'll cover a couple of things here. So we'll zoom in on the machine, on its cleaning action, and on this print, and talk about a few things there. Okay, so the machine's just about finishing up the first portion of the PVA, and it'll do a tool change now to tool 5. And what we're going to watch for here is that there are no globs on the nozzle. The nozzle comes down clean, and then the print head immediately starts printing when the extruder comes into contact with the part. Now in this case, you can see we left that one little string, and now actually we're pulling up strings as we go around the print. So the problem here is the adhesion of the PETG on the PVA. So what we'll want to do is slow down that first layer of PETG print. So let's just stop this print now and go back and make that change. So we need to figure out what layer that the first section of PETG that we're printing happens on, and then we need to change the speed for that layer. So if we look at our settings and simplify for PETG, we do have this ability to change our first layer speed. But unfortunately, this only works if our first layer is actually the first layer of the print. It doesn't work when we're doing multi-material prints and our first layer occurs at some height above the first print layer of the entire print. So we can't use that. But we can use our post-processor to slow this down. So we'll look at how to do that first. So one way we can find out which layer that first PETG layer happens on is to just walk back in our preview and see when tool 5 is first used. And we can see it there. It happens at layer 8. So then when we save this file, we'll overwrite the old one again. And then we'll go into our post processor and leave those settings the same, grab our file, and now we'll use the speed reduction here in the post processor to get what we want. So our layer number was 8 that we saw from the preview, and let's slow that all the way down to 30%. Let's see how that does for us. Now, another option in Simplify 3D would be to come in here and go create another process and make one of those processes just the first layer of PETG. And we could set the start printing at height and stop printing at height to be that first layer, and then for the rest of the print, do a second process that would start after that layer. That's a little bit clunky. I'd rather just use the post processor. So let's start this print. Okay, so while that's printing, let's look at what actually happens when we do a tool change. So let's start by just looking at our G-code file. And if we scroll down, actually let's search Control F for T prime 5. So this T prime 5 code is what the post processor inserts for an auto clean cycle. So after it finishes doing the printing portion with the previous tool, it's going to call up a tool change. So this G10 P4 R150 is setting our standby temperature for our tool 4, or sending tool 4 into its standby temperature. And then we get this M98, which calls up a subroutine, this T5'.g, and that's where our tool change happens. So let's go back to our machine. And then just a quick note, in order to get familiar with the G-code that this machine uses, if you just search for Duet G-code wiki, so the Duet board is what we use to control this machine. And they have this extremely useful G-code list that has all the explanations for the different codes that they use available to anyone. So as you're learning how this machine reacts to the G-code, this is just an extremely useful resource. So let's go to our settings menu, then our system editor, and we'll scroll all the way down till we find this T'.g, or T'5.g. So this is the subroutine that the machine runs when it sees that T'5 command. And we don't need to understand everything that's happening here, but we should at least walk through a little bit of the primary function of the cleaning station and how it's called up by the machine. So the first thing that it does is save the current position so that it can come back to it later. And then it moves the bed out of the way. So if the chips do fall down and are not captured in the arm, they at least don't fall into the print region. Then it rotates the turret so that the nozzle that we're going to clean is in the prime position. So that's what this G1 U217.3 command is. So it's saying G1 is just move this axis at a specified feed rate. That's what the F9900 is. That's 9,900 millimeters per minute. And U217.3 is the position that we want the extruder at for priming the nozzle. And then this G4P20 is just a pause. Then this M116P5S10 is saying wait until tool 5 is up to temperature within 10 degrees of its set point. Then this M42P20S1 turns on the solenoid that brings the cleaning station out. So this is the main actuator of the cleaning station. So this G1E10 F6000 is just a makeup for previously retracted filament. Then down here, this G1E15 F300 is a much slower extrude when we're actually priming the nozzle. So this E15 is extrude 15 millimeters of filament. And then down here, this G1E -9.5 F6000 is retracting 9.5 millimeters of filament. So in summary, to prime the nozzle, we're bringing out the prime surface, making up that 10 millimeters of previously retracted filament. Then we're extruding 15 millimeters of filament. Then we're retracting 9.5 millimeters of filament. And then we're moving the nozzle down here to the actual cleaning location. So this G1U228.4 is the location that the extruder needs to be in order to be aligned with the blades of the cleaning station. Then if you have a vacuum connected, this is what will kick on the vacuum. This clean.g, this is what is actually the action of the solenoids of the cleaning station in order to clean the nozzle. And then we hold the blades closed so that if there's any string coming from the nozzle, it won't pull that puck that we extruded onto the prime surface and then cleaned. It won't pull that back down into the print. So with some stringy materials, that can be a problem. So we're holding the blades closed while we move the nozzle back into position. And then we do what we call a post-clean of the blades, which is just kind of chattering them to drop the puck of material into the arm and be sucked away by the vacuum. Then we're turning off the vacuum. So it's a mouthful, but that should give you a feel for what's happening at the cleaning station and which parameters we can actually adjust to dial in the cleaning action. So as we're trying to get the performance that we want out of the priming function, we'll come back in here and make a few changes, especially to this value here, this final retraction before we go to clean the nozzle. That feature is key, and then this value, this E15, the actual extruded volume to create the puck of material that we clean off of the nozzle, those two values are the ones that we will dial in the most in order to get consistent cleaning station performance. Okay, let's look at what's happening in our print. And we can see that we're getting a pretty clean print, and this is PVA that's being printed now. We're not getting any globs of material at the start or the end of the print. There's a little bit of stringing, but that kind of always happens with PVA when you lift the nozzle straight up off of the part. So we're priming the next print head, I think T5 now, and we'll see as that comes down if the nozzle is clean and if it starts printing right away. So that does look pretty good. So let's try to go in the other direction. So let's go down to our T'5.g again and edit this. And now let's come down to these parameters here. So we have our volume of extrusion that we do for the prime. So that creates the puck of material, and then we have this retraction amount. So let's reduce this and see what happens in the print. So let's take this all the way down to -5.5 and save the changes. Okay, so here we go. This is T5 priming now. And I'll show you the actual cleaning station action in a minute. So it's hard to see there, but on the back left corner where it started the print, it created a blob of material when it first started extrusion. So by doing iterations like this of adjusting those values in our T prime function, we can dial in the timing of the extrusion and retraction in the tool changes just the same way that we dial in retraction in our print. So extrusion printing is all about timing. There's no valve that turns on or off flow. We have the drive rollers that push the filament down into the hot end, and then that filament acts like a plunger to create pressure in the hot end. And the way that the material responds to that pressure is dependent on the material properties and on the temperature that we set. So we have some knobs to turn in order to dial in the timing and the action of the extruder during a tool change to get the flow to start and stop as we want it to. A couple of other things worth noting when we are tool changing on the H series is that when we run the post processor, we have these preheat times that we set for the different tools. Now, in order to apply these, the post processor is counting back in time in the G code and inserting a line to preheat the tools. So at least this much time has to have elapsed since the last time we used that tool. Otherwise, this code will get inserted in the wrong place. A couple of things that define this and simplify are, one, the geometry of the model. So if we have small features that extend upward next to each other that are different materials, or different tool heads at least, used to print them, then we need to pay attention to our minimum layer time in our print. So here in the speeds tab, this adjust printing speed for layers below. In this case, I have it set to 10 seconds. So for certain prints, you're going to have to play with this value in order to not have too many tool changes too quickly, because the cleaning station is also a solenoid-driven device. So if you're running that cleaning station every 5 seconds, it will overheat and it will stop working correctly until it cools back down. So if this becomes an issue, there are ways to add cooling to that region, whether running your vacuum for longer or adding a fan to that zone. But in general, it's better to overcome this by just adjusting your minimum layer times here. And if you do have a part where you need to do frequent tool changes, and it's not going to be much time in between them. So say you're printing lettering that's all different colors or something like that, then you can just get rid of these auto clean functions and let the machine tool change without doing the priming cycle. Okay, so that print finished, and our overlaps look good. We have a little bit of extra material on our urethane, but it's nothing I'm worried about for this print. And the top section there looks smooth. It looks like our Z offsets are correct. So let's go ahead and move forward to our final print.